We're going to continue our discussion today about chair cyclohexane. And I want to show you why we should care, because at some point you've got to be concerned about how boring it is just to draw the same shape again and again. And the reason why this is important has to do with the fact that in biology, structure and shape is intimately connected to function. So I'm going to draw here, and you don't need to bother copying it down. This is just to illustrate for you what's the basic principles here. I'm going to draw a chair ring. This is a 6-membered ring containing an oxygen. It's not cyclohexane, but it still adopts a chair, and it's a carbohydrate, one that you may be familiar with. It's glucose, and it's a glucose molecule connected to another glucose molecule in a very specific way. I've got to fill in some hydroxyl groups to make the molecule complete. Each of these chair subunits is a glucose molecule, and notice that all of the groups on carbons 1 through 5 in both of these subunits, all of the groups are equatorial. In particular, the way that these two sugars are linked to each other through this central oxygen is equatorial on one side and equatorial on the other side. All right, this happens to be the structure of cellulose fiber or plant cell walls. Okay, roughage, lettuce, kale. Ugh. Man, I tried. I'm trying to be more healthy. It's not going very well. I look a little different in my 42nd year than I looked in my 22nd year. You can laugh, but it will happen to you too. And as in an attempt to get a healthy and savory snack, I tried to make some kale chips. It was disgusting. I know there are people who swear by it, but it was absolutely disgusting. Anyway, cellulose is in plant-based foods. Now we can take the exact same subunits, still glucose subunits, but we're going to connect them together with a slightly different shape. Now, instead of being connected through an oxygen that is equatorial with respect to both rings, if we instead make the connection axial on one ring, notice that this OH group is at an axial position relative to carbon 1 of the subunit on the left, whereas the oxygen highlighted in orange is at an equatorial position relative to carbon 4. This is a subunit of starch. Okay? Dramatically different nutritional uses, right? They tell me that cellulose is a green food and I can eat as much of that as I want because it fills up, but my body doesn't have the enzymes to hydrolyze that linkage that's equatorial on both sides into glucose, so cellulose does nothing for my blood sugar, right? And it's because this shape doesn't fit into the enzyme that hydrolyzes starch. In contrast, you've got enzymes in your spit and in your guts that are really good at hydrolyzing this linkage. If you don't believe me, go suck on a saltine cracker for a few minutes and you can start to taste sweetness. That sounds like a great insult. Go suck on a saltine cracker. In any case, the reason it works is because you've got the enzyme to hydrolyze that linkage and it's got that particular shape. So shape means everything in biology, and so that's why we're bothering to learn about shapes of organic molecules. Now, I wanted to just review a few things about chair flipping or flipping chair rules, whatever. And this maybe is best if we have a cyclohexane that's attached to two different things. So here is the overhead version of trans 1,2-dimethyl cyclohexane. In going from a overhead view to a more realistic picture of the molecule's conformation, it's useful to number atoms of the ring and to do so in the same sense. In other words, if it's clockwise around the ring as I go from 1 to 2 to 3 and so on, in my chair I need to use the same sense. That may not make any sense to you now. Stay tuned. In chapter 5 you'll see that it makes a big difference. I notice that as I've chosen to put carbon 1 at an up carbon position, the substituent on carbon 1, the methyl group, is down, and at an up carbon, the down position is equatorial. So I put the methyl group in that equatorial position. I could also put in the hydrogen that's implied but not shown in the drawing on the left. Similarly, at carbon 2, in the way I've chosen to number these molecules, or these atoms of the ring, carbon 2 is a down carbon, and at a down carbon, the up position is also equatorial. So that's where our methyl group is, and then the proton that's implied in our drawing on the left would be down axial. So it will be a useful skill for you to start with a structure on the left that is an overhead view and get the sort of from the side chair depiction of the molecule. Go ahead.
Does it matter, like, when you are numbering it, where you start on the chair confirmation? Because if you start like just one carbon to the left, then it would be axial.
Exactly. Good point. The point is that my choice of where to put carbon 1 in my chair drawing actually determines whether the group on carbon 1 that is up is going to be equatorial or axial. And so, no, it doesn't matter which one I started with. If I go the other way and put carbon 1 at a down carbon and then carbon 2 at an up position, then, going back to my original drawing, at carbon 1, the methyl group should be down. When carbon 1 occupies a down position in a chair, the only down substituent is the axial one. And similarly, when carbon 2 is at an up position in the chair, the substituent on carbon 2 that is up has to be axial. So I think this is what you were noting, that if I had put carbon 1 at a down position, both of the substituents would be axial. So the question is, which of these drawings is right? And the answer is yes, because one of them is one chair and the other is the other chair. Okay? And they're in equilibrium with each other. And we need to talk about how you determine which one is the most stable chair. All right? But first, I want you to note some things that happened when we went from one chair to the other chair. Up carbons become down carbons, and vice versa. Down carbons become up carbons. Up substituents, that is, things coming off the ring, stay up. Methyl group was this methyl group was up here. It is also up there. Down substituents, how many times can I write substituents? Stay down. But axial goes to equatorial, and equatorial goes to axial. All right, so it's a lot of things to keep track of, but you need all of those in order to get the chair right. Up and down do not change. The only way to change up versus down is to break bonds. In other words, this molecule is different. The one I just drew at the bottom is different from the one I drew at the top. It's easy to see that that's the case when you view from overhead. Here the methyl groups are trans to each other. Here the methyl groups are cis to each other. But it might have been tempting for you to draw a chair form of the cis dimethylcyclohexane and to think that you could somehow interconvert between the cis and the trans, and you can't. Okay? This is one chair of the cis dimethylcyclohexane. I'm going to draw the other chair. Note that up stays up and down stays down. And notice that what I've drawn here for the cis isomer is not at all the same as what I drew up here for the trans isomer. You've got to get that. Up stays up and down stays down. And all of this assumes that we're keeping our orientation relative to these molecules the same. That is, for the molecule on the left, we're viewing it from the top down, overhead, and then, sorry, I gotta move my starch molecule. And then this hovering over the molecule would have been where our eyes were to get that overhead view. Yes?
Can you just move the voice thing?
Oh yeah, sorry about that. Is that better? Okay. So we'll talk in chapter 5 actually. There's a name for molecules that have exactly the same connectivity, but are nonetheless have different shapes. You've used it before when we were talking about alkene isomers, cis and trans. The term is stereoisomers, and that refers to molecules that have their isomers, same molecular weight, same molecular formula, same atoms attached to each other in the same configuration, except the shape is different. Stereo is referring to like 3D and not stereo surround sound or whatever. But all right, so the chair rules. The chair rules are sort of listed here, and you need to get good at that. Cis and trans are stereoisomers. The two chairs are just two different conformations of the same molecule. So two conformations of the trans stereoisomer. And these are two different conformations of the cis stereoisomer. Some people will call conformations of the same molecule conformational isomers, or conformers for short. You can do that. It's fine, but it may be a source of confusion because they're just the same molecule, just rotated. So no, we would not say that the one chair and the other chair are stereoisomers of each other. They are two different conformations of the same stereoisomer. Yeah?
Would you ever ask us on a test if they were different isomers?
Would I ever ask you on a test if these two were different isomers? I could ask, are they different molecules or are they the same? Yeah. We're going to, at the temperatures that we live at, the conformations are interchanging, and so you can't separate out one from the other. And therefore, we're gonna say that they are the same molecule. That is, these two conformations are the same molecule. They are two different conformations of the trans stereoisomer. These two here are two different conformations of the cis stereoisomer, but the cis and the trans stereoisomer are different molecules and have different properties. Okay. Now, so go ahead.
Can we just go over real fast what makes the down and the up carbon? I'm kind of confused on what that is.
What makes a carbon up versus down? I don't have a really good way to, maybe up and down is not the best word. Up carbons I'm going to highlight in, I don't know, purple. They are carbons where the two lines of the ring sort of make a mountain peak pointing upward. And the down carbons, which I will highlight in, I need a better color. I don't know, this weird pink, which actually looks too much like purple, so never mind. Orange. Those are down carbons because they occupy valleys, sort of where the two lines of the ring in the chair point downward.
Okay, so when you turn it, we say that the up carbons become down carbons. What is
Okay,
just because then the one carbon is in the down position?
right. So it's a really interesting question about how we get from here to here, because it looks like all I did was just move numbers. And that's because it's really hard to show three-dimensional rearrangements on paper. When a chair flips, what happens is we're gonna take this up carbon and the two adjacent down carbons. The up carbon we're going to flip downward, rotating that group downward, and the two down carbons we're going to flip or rotate upward. So thinking about what that will do, if we rotate up carbon 1 in the downward direction, that should take the methyl group that was at a down equatorial position and push it to a down axial position. Similarly, on the other side of the molecule, we're going to take, this down carbon, and we're going to move it upward. And then we'll take the two up carbons and shift them downward. And for, say, the down carbon, the groups that were attached to it are both protons, but it's this proton that used to be up equatorial that's now going to be up axial. The challenge in doing that is that I've not found a good way to draw a chair with an up carbon in the lower left corner. I suppose you could do it that way, and you'd have to sort of squint at it and make sure that you know that the thing that's on the top is actually in the front. It's kind of like that weird thing where you try to draw a cube and then you see if you can make your eyes see the back side of the cube as the front side. Have you ever done that? So it's an issue of perspective, and to avoid that challenge of having to draw an up carbon in the lower left-hand corner, what we do is we flip the chair and then we rotate it a little bit. So no, it's not like we just turned the molecule around. We did the chair flipping and then adjusted it to make it so that we can draw it easier. Yeah, you bet. Some people will draw chair flipping like this because, and I think your text will do this. But that, if you, if this is carbon 1 and this is carbon 2, that's not a chair flip, that's just a twist around to see one from the other. So even when they do draw the chair from a totally different perspective, you're going to find that they also shift the positions of the carbons. So if your text does this, they're just trying to communicate, oh, we've done the chair flip. And I'm doing the same thing too, only I'm not twisting the molecule as far as them, but it's basically the same thing. Okay, so we were going to talk about stability. Jake, at home, you're noting that an equatorial position is more stable because there's steric crowding in the axial position, and that's true. So let's just let's take a step back before we worry about which of these two chair conformations is different in energy or lower in energy. Let's take a step back and let's just look at a cyclohexane molecule with just one substituent on it. And we want to make sure that you understand why it is more stable to have the methyl group in an equatorial position than in an axial position. So there's two ways to think of this. First, 1, 2, 3, 1, 3, 5. When the methyl group is in an equatorial position, it's fairly close to up axial substituents on carbons 3 and 5. And I forget what your text calls these 1,3 diaxial interactions because relative to the first carbon you move 2 bonds away, and the methyl group is very close to the axial substituent on that carbon that's just 2 bonds away. So that can be kind of a problem. And if we go to the Spartan app, delete, and just draw that cyclohexane and then ask it to show us the two different conformations. Here's the equatorial conformation, here's the axial conformation, and if you look at that chair, you can actually see that that methyl group isn't perfectly axial in this molecule. It's actually leaning away from the methyl group is leaning away from the other axial substituents on carbons 3 and 5. So you've got that, and that is just steric repulsion. It's electron-electron repulsion between the electron cloud surrounding the methyl group and the electrons surrounding these other substituents. Steric repulsion, steric strain, you want to call it that, that's fine. There's also a torsional strain argument. And to see this, what we're going to do is we're going to look down the bond between carbon 2 and carbon 1. And it's been a while since I drew the evil Sith eyes, so we got to keep that one alive. I'm going to draw a Newman projection starting with carbon 2. From our perspective, at carbon 2, there should be, this is the equatorial proton, this is the axial down proton, and then here is atom 3. And we'll just put atom 3 there on its own. We know that atom 3 is attached to other things, but we don't need to draw it out. Here is the methyl group that's up axial on the back carbon. And here is atom number 4 that's part of the ring. And these two are, 3 and 4, are connected by the rest of the ring, which we're not drawing. Okay, let me just pause there. Is everybody okay with that drawing? What do you notice about the position of the methyl group relative to atom 3 on the front carbon. What is the relationship? Go ahead.
They're gauche.
They are gauche to each other. Good. The dihedral angle theta here is 60. They are gauche to each other. And Hallie from home, I said that the having the methyl group equatorial is more stable for reasons we're going to talk about. Yeah, so the methyl group on carbon 3 is gauche. I'm sorry, the methyl group on carbon 1 is gauche to the ring atom on carbon 2. It's attached to carbon 2. There's a gauche relationship. Now, it turns out that we would see the same thing if we looked down the bond between 4 and 1. We would see that there's another gauche interaction as we look down that bond. Let's, now this is going to be tough. Let's start with the equatorial conformation, and let's again look down the bond between 2 and 1. And so you sort of got to put your nose in the plane of the page and look down that bond. From that perspective, here is the axial proton on carbon 2. Here is the equatorial proton. Here is atom 3 of the ring. And then in the back, carbon 1 is attached to an axial down proton and an equatorial up methyl group. And then here's, oh, I'm making stuff up, aren't I? And then here's atom 6 from the ring, and those two are attached to each other. Notice now where the methyl group is in relationship to the ring atom on the front carbon. Now they're anti to each other, right? So it turns out that having a substituent equatorial is more stable because it relieves 1,3 diaxial interactions, diaxial steric repulsion, and it also relieves torsional strain, by which we mean gauche in the less stable conformer turning to anti in the more stable conformation. Yeah?
So in the first conformation to the left, the two hydrogens to the right of carbon 2 are both equatorial, right? And
The two hydrogens to the right,
are both equatorial.
yes. So this is on carbon 2, the equatorial up proton. This is on carbon 1, the equatorial down proton.
If those were both substituents, like methyl substituents, would that also be a gauche angle?
Yeah, so it's a good question. What if I had other things here that were not hydrogens? What if there were other groups? At that point, it would become more difficult to describe gauche versus anti. We're not going to use those terms in an absolute sense. Instead, we'll say the relationship between these two groups is gauche. So it would still be true, no matter what we did here, that this methyl group is gauche to atom 3 of the ring. Okay. Why is the axial, yeah, I totally screwed up there. There's a comment on my numbering scheme for the axial molecule. Yeah, I'm sorry, I fixed it in one place but not in the other. Apparently 4 comes between 3 and 5 instead of between 5 and 1, for whatever that's worth. Okay, so a couple of reasons why axial substituents are, having axial substituents is less stable than equatorial substituents. Now, it turns out that you can measure, in solution, you can measure the difference in free energy between these two molecules. Remember, when we say more stable, we mean something has lower free energy. So you would expect, in going from the axial conformation to the equatorial conformation for that methyl group, that you would be going downhill in free energy. And in fact, yes, the free energy of that process is about Why memorize things that you can look up, right? So you don't waste time in class. That's why you memorize things. It's about 1.7 kilocalories per mole, more stable to be in the equatorial conformation than in the axial conformation. And yes, lower free energy means more stable. This is actually the origin of the A value. A referring to axial. The A value tells you how much worse it is to have something axial versus equatorial. So the A value actually presents these numbers in reverse. It says how much worse axial is than equatorial, or in other words, the A value presents the change in free energy from going from the equatorial conformation to the axial one. And there's a bunch of substituents listed in your study guide, and we'll just point out a few. Hydrogen, of course, is 0, because if cyclohexane is, everything is hydrogen there, the two chairs are identical, right? If it's the methyl group attached to one of the carbons, then the A value is 1.74. And as you start to increase the bulkiness of the group, the A value starts to increase. Interestingly, as you go from methyl to ethyl, you put another carbon on that equatorial position, it doesn't get as bad as you would think. And the reason for that is that we can still rotate around carbon-carbon bonds. So the methyl group will actually orient itself so that it's pointing, the ethyl group will orient itself such that the extra carbon is pointing away from those diaxial protons, so it's not as big of a deal. And when you go to ethyl, it only appears to increase in size by 5 hundredths of a kcal. Someone's asking again, what is the A value? The A value is a measure for how big a substituent is, but it's derived from measuring the equilibrium constant from a cyclohexane that has a group on it, and you measure the difference in energy between axial and equatorial conformations. As you start to add more carbons to that first carbon attached to the ring, for example, if you use this sort of V-shaped isopropyl group, your A value starts to jump. And if you go to the carbon attached to the ring, that carbon is also attached to 3 other methyl groups, then you get to an A value of like 5 or 5.5, I think is what the table says. By the way, we call these substituents sometimes the tert-butyl or T-butyl group, and this one the isopropyl group. You don't need to memorize those names, though I will use them in class to guide our discussion, and so it might be useful to be familiar with those names. So you would predict that having the tert-butyl group equatorial versus axial is more important than having a methyl group equatorial versus axial. Yeah?
So if you have like just a bunch of different groups on a ring, could you just like kind of add up these different A values to figure out which one would be more stable?
Yeah, the question is, if you have multiple things on the ring, can you sort of add and subtract A values to get an idea of which conformation is more stable? Qualitatively, yes. Of course, as you introduce more complexity, there's other issues and adjustments the molecule can make to resolve unforeseen issues. But for example, this would allow us to easily predict the relative energies of these 2 chair conformations for the trans dimethyl cyclohexane. So you've got one chair versus the other chair for the trans stereoisomer. Which is more stable, the one chair or the other chair?
The one chair.
One chair should be more stable. And you know this because of what we've talked about. If I were to ask you how much, more stable it would be? What might you predict? By that increment, but probably twice since there's two of them. Now, I'm not going to have you do, it seems silly to have you look up numbers and then multiply them. But you should be able to tell fairly quickly that the one chair conformation is quite a bit more stable than the other chair. How about for the cis stereoisomer? What do you predict for the difference in energy between one chair versus the other chair? Go ahead, sorry.
Actually, so with the one chair, why isn't there like interactions between the two methyl groups in the equatorial positions?
With the first chair, why isn't there interaction between the two methyl groups in the equatorial position? Yeah, this is a good question. If you look down the bond between 2 and 1, it is true those methyl groups are gauche to each other, but each is anti to the ring in either direction. In contrast, when they're anti to each other, each is gauche to the ring in both directions. So there are offsetting factors that get you to this conclusion. Although I think you're absolutely right. Probably the difference in energy isn't as clean as that 2 times 1.74 or whatever, for that very reason that you're discussing. This one is probably not as stable as you would expect because of that reason. But you don't need to be able to reason through that, at least not in an exam situation. Okay, for these two chairs, what do you think? Which one is lower in energy? Yes and no, they are the same, right? Each has one axial methyl group and the other has, and each has one equatorial methyl group, okay? And so you would expect at equilibrium to have sort of a one-to-one mixture of these two. Go ahead.
Would it matter if they were an up axial group or a down axial group?
Does it matter if an axial group is up versus down? No, not in this particular molecule. If we had another substituent also pointing down, it might. But in a case, as we've got here with this example, no, the two methyl groups are actually identical. In fact, if you want to do the pancake flip on this molecule, flip it over, it's the same thing. So those two methyl groups attached to carbons 1 and 2 are actually the same. Okay. Kyle at home is asking whether, like, if we had two OH groups and there might be some potential for hydrogen bonding between the two OH groups in the equatorial conformation, would that make the equatorial conformation more stable? Sounds reasonable to me. Would I expect you to predict that? No. All right. So let's just do a couple more examples. Let's make, we'll start with looking at the molecule from above. Let's put an isopropyl group here, and then let's put a bromine there. Let's draw a chair, and then we'll draw its counterpart, the other chair, and then we'll see which conformation we think is more stable. Doesn't matter where you start number in the ring as long as you do it consistently. Doesn't matter where you put a number in the chair diagram as long as it's in the same spot relative to all the other numbers in the chair. As I'm going around the ring clockwise here, I have to do the same thing here. At carbon 1, I've chosen my to draw my chair with carbon 1 at an up position. I'm just predictable. Bromine is down at carbon 1, so all right. Carbon 1's down position happens to be equatorial. Now I need to go around to position 4, where I've got an up isopropyl group. At carbon 4, what is the up position? Is it axial or is it equatorial? It's equatorial, so I'd put that isopropyl group there. All right, looks pretty good. Both are equatorial, that's fun. Let's now draw the other chair. which we do the ring flipping as we've discussed. At carbon 1 now, in the other chair, the down position is axial, and at carbon 4, the up position is equatorial. Which one is more stable? Easy, right? The one where everything's equatorial. Okay, but what if we made it so that the bromo was up instead of down? Then all we have to do is draw the same chair again, only we switch bromo from being down to up in each of the two chairs. Now we got a choice to make, right? Because in the one on the left, bromo is axial and isopropyl is equatorial, whereas in the one on the right, bromo is equatorial, isopropyl is axial. So, which is likely the most stable? Well, you got to go and look at your A values if you don't know, if you don't have a good sense for how big the bromo group is. And if you go look at the A value for bromo versus isopropyl, for bromo it's actually 0.38. For isopropyl, it's 2.6. So first off, the data tell you what? Which of these two, having bromo axial versus equatorial, which of these two options for the stereoisomer below, which one is better? Isopropyl equatorial. You can tell that from the A value, right? Now, I guess we should point out that bromo is a couple rows down the periodic table from carbon, and so bromo is bigger than carbon, and radius should count for something, and yet bromo shows up as having an even lower A value than a methyl group, which had an A value of 1.7. And in fact, if you look at the A values of the halides for, say, fluorine, chlorine, bromine, and iodide, it's really weird. Fluorine is really small, almost as small as a hydrogen. It's basically a 1-to-1 toss-up between axial and equatorial conformations for fluorine. Chlorine gets a little bit bigger. Bromine is actually a little bit smaller than chlorine in this experiment, and iodide is about the same as chloride. What you've got going on here is true, you have increasing size, but you also have increasing bond length. So if we go back to what makes the equatorial conformation better than the axial conformation, you can imagine that if you increase this distance here, the 1,3 diaxial interaction should matter less. Similarly, if you increase this distance here, the gauche interaction with the ring should matter less. And so you've got two offsetting effects that compensate for each other. And so the halide series is kind of weird. Once you get past chlorine, it's all sort of the same. So this highlights an important point that sterics is not only about size of a group in a sort of volume sense, but it's also about bond length and how close that group is to other groups. And so you need to, and it can be interpreted, you should interpret it with caution. But be able to solve these kinds of questions where I draw a molecule in sort of this overhead view, and then I say which of the following is the most stable chair conformation. And beware, each cyclohexane molecule only has 2 chair conformations, so put our test-taking skills hat on. If a question asks which of the following is the most stable chair conformation of this molecule, and there's like 8 options, guess what? 6 of them can't even be the right molecule, right? Because there's only 2 chairs for each molecule. So part of your skill here is not only recognizing which chair is more stable, but also faithfully recapitulating in the chair the up-down relationships from the overhead view. all right? Let me show you a particularly onerous problem. Dun, dun, dun. All right, carbohydrates. Beautiful 6-membered rings and complicated structures. So, let's see. Dun, dun, dun. No, sorry. All right. That is a carbohydrate. 1, 2, 3, 4, 5. And I guess oxygen doesn't need to be numbered. So I'm going to draw you some options in no particular order. You should not assume that the first option I draw you is the right answer, just as you don't assume that A is always the right answer on an exam. Dun, dun. Like I've said before, I am evil, but I do disclose at least some of my evil tricks in advance. And, you know, we could go on all day actually, but I think 4 options is enough to be getting going with. Yeah. Okay, fine, I'll do one more. Okay. A, B, C, D, E. So, I might ask you, and here's what people typically do if they're not very thoughtful about this kind of question. I would ask the question in this way: which of these is the most stable chair conformation of molecule 1 or I or Steve, I don't know, or actually galactose? No, yeah, galactose. Which of these is the most stable chair conformation of galactose? And it turns out this problem is not really a problem about stable chair conformations at all. It's a problem about, can you get the up-down relationships from the overhead view correct over here? And then once you've got them correct, can you then identify the right chair? Okay? So, some people choose A immediately because, oh look, all of the groups are equatorial and that should be the most stable. But A is not correct because A is not even the same molecule as galactose. Okay, now take a minute and look at that and see if you can figure out why A is not even the same molecule as galactose. I will help you and number the carbons a little bit. Focus on the principle that no matter what chair you're in, up stays up and down stays down. It's diabolical. Dastardly, Dr. Price. Okay, so someone in the chat says that substituents at 1 and 2 are trans to each other in A, but are actually cis to each other in galactose. Good. That's one of the ways you can foil my evil plans, is to look for consistent relative relationships between OH groups. Notice, yes, the OH group on carbon 1 and carbon 2, they are both down. Therefore, they have to both be down in the chair conformation, and actually that one is up. Okay? Can you spot another problem with molecule A? Same sort of thing. Carbon 4 is up here but down here. All right? So, good. You successfully foiled that particular distractor. I actually drew for you glucose, not galactose. Now, take a minute and sort through. Oh, we're past time. Sorry. You should have said something. So, in the meantime, sort through these, and we'll pick up next time with what the right answer is.